So good afternoon and welcome back to the class on smart materials and structures. So in the morning we had started with the module related to our MEMS. What do you mean exactly by micro electromechanical system? And we also dealt about the various basic concepts. What are its micro components? What are its applications? What is the need basically to analyze the mechanical properties of MEMS, right? So now we need to move further related to which are the basic mechanical properties. We need to study in depth how to evaluate its properties when MEMS device need to be made. So based on that, we have to start right from the elastic properties, right? So why we need to focus on elastic properties? Because elastic properties are directly related to the performance of the device. It mainly depends upon how flexible your device is, what is its elastic nature, right? So based on it, the yield or performance of the device could be evaluated. And hence it is very much essential for anyone to know the elastic property of the material what you are using to make a MEMS device. So under elastic property, you know very well when you have a stress strain curve. So the variation with the stress and strain usually yields with the Young's modulus and also the Poisson ratio. So elastic property in the sense you should be knowing what is the Young's modulus and the Poisson ratio of the material what you are using, because these two terminologies are directly related to the elastic property of a given material. And hence, whenever elastic property comes into the mind, you should think about what is its Young's modulus and the Poisson ratio, because this mainly governs the mechanical behavior of the device. So for that, you should be very much keen in determining these two values. So once you are clear about what are the properties you need to evaluate, you should see that which are the independent and the dependent variables. Okay, so here Young's modulus and Poisson ratio. So both are independent mechanical properties. What you have to evaluate. Okay, and these two independent properties are very much essential for determining the definition of the mechanical properties of the material. So whenever they tell it is the mechanical properties associated with elastical properties, you should tell about which are the two independent mechanical properties. So these are Young's modulus and the Poisson ratio. So based on the Young's modulus and Poisson ratio, you can tell what is the accurate properties you are giving for that particular device, right? So this has to be cleared before one start with any device. So in that aspect, you have to evaluate the value of Young's modulus. Anyone can tell me what is the like how do you define Young's modulus? Anyone can let me know how do you define Young's modulus? Sandesh, you're there?
Yes, ma'am.
Yeah, how do you define Young's modulus?
Change in length.
Louder.
Change in length, ma'am. In
Hello. You're not audible. You're not audible. Danush, you're there?
Yes, ma'am.
How do you define Young's modulus?
Ma'am, it is the ratio of stress by strain, ma'am.
Yeah, basically it is a ratio of stress versus strain. It easily gives you what is the material stiffness. So if the given material is too stiff enough, so then even though the load is subjected on it, it will not be induced to large amount of stress and strain. So based on the value of Young's modulus, you can define how good the material stiffness of a given material what you have selected for MEMS device. So usually we extract the experimental value for Young's modulus from the slope of stress strain curve. So stress strain curve are familiar to everyone right from your UG, right? So you are aware about Young's modulus also, how do we define and how do we extract also from the graph. Mainly you have to think you are calculating the material stiffness of a given material, so that we can get directly through Young's modulus. So the value we get from the graph of stress strain curve. So this you have to remember. Apart from that, we were speaking about the Poisson ratio. So Poisson ratio is also depending upon the lateral expansion or contraction which has been happening with respect to subjection of the load. So any variation in the deflection, it could be either compression or expansion. So this deals with respect to the lateral deflections. So these lateral deflections are provided by our Poisson ratio. And this usually comes into picture when you're subjecting it to an axial stress. Means you need to apply a load in axial direction. So based on the axial stress induced in the body, this expansion or contraction comes into picture. But we are focusing this within the elastic range. Please do consider when you have a stress strain curve, you have an elastic range and then the plasticity comes on. So once the elastic range has been crossed, the deformation which goes further could not become back to its original position because it has crossed its plasticity. It has crossed the elastic region and moved into plasticity. So what we are speaking here with respect to the values is associated with respect to elastic region only. Why? Because we are focusing on the elastic properties of a given material. Okay, so you should not take any values which is outside the boundary of elastic region. So that you have to keep in mind. Okay, so based on this, we have a figure 1 of a circular membranes, right? So here if I show you, this is the circular membrane what we are using. So using this circular membrane, so you will determine the load deflection technique. So by subjecting the circular membrane here, and if you apply the load in axial direction, so what is the deformation which is coming into picture? So that could be evaluated within the elastic range and after the elastic range has been crossed. So we will focus the data only within the elastic range. And remember, when I say a circular membrane, it will be having a thickness. And since it is a MEMS device, it cannot have the thickness more than 1 millimeter, right? It could be minimum 20 microns to upper limit 1 millimeter, not above that. If it is above 1 millimeter, then you cannot term that to be as an MEMS device, which is of microstructure. So every membrane, whether it is a circular membrane or whatsoever, it will be having its own thickness of negligible value, which is falling within the given range. So here the same thing is tested by taking a circular membrane. It is subjected to axial load, and based on the deformation you will see what is the lateral deflections you are getting, and then you will find out the Poisson ratio also. And there is a derivation for pressure deflection behavior of a circular membrane. It was being invented by the person Suchiya in 2008, but you don't have any derivation in your syllabus because you have a title called mechanical properties. Under that you have to focus on elastic, inelastic, strength and tension also, right? But there is no derivation as such. So you will neatly write any variation, the deflection which comes into the circular membrane due to the pressure is expressed by this equation as shown to you here. So you have to just write this equation. So this pressure variation will come across depending upon the axial load what you are subjecting. So based on the axial load, right, the pressure will be distributed across the membrane. So this pressure will show you the variation which is coming across the circular membrane. So that is given by this equation. So it will be 4 sigma naught into T divided by A square into D plus 8 ET divided by 3 into 1 minus mu into a to the power of 4 into dq. So this is the equation what you have to write down. So once you write down, you can tell what are each parameters are. So P here stands for the pressure which has been applied, so that you are aware of. And then you have A, T, E, sigma dot, sigma naught, and V. So these are associated with the radius. So if you see the circular member here, I've shown a direction of line here which is passing through the center, and instead of writing R, it has been mentioned as A. But still it is the radius of the circular membrane. So A stands for the radius of the circular membrane. T stands for the thickness of the circular membrane. So what is the thickness of the membrane we are using? And E, you are aware enough, it is the Young's modulus. And sigma naught here we refer for the Poisson ratio, right? So you have to be aware about what does each term stands for. So this much you have to write if they ask you to explain the elastic properties of a given MEMS device. Usually they don't be specific for the particular one. They just ask you to write a note on mechanical properties of MEMS device. So you should then list out what is the need for the study of mechanical properties of MEMS as I explained in the previous class. So then you should mention what are the mechanical properties what you have to evaluate, list down one by one, and then you should start explaining, right? So this is about the elastic properties. So once elastic, any doubt related to elastic properties? Is it clear or should I explain anything related to it?
No, ma'am.
Okay, so once elastic properties are being clear enough, so you need to go to check for the next one, that is due to internal stresses. So one thing you have to keep in mind, whether it is an MEMS device or a regular device of an actual scale, when you subject it into an axial loading or any type of loading, the stress will be induced in the body. It depends upon what is the amount of load which has been subjected into, right? So due to this, internal stresses will be always developed. If the material is not able to withstand the stress, then it results in the deformation and even strains comes into the picture. So you should evaluate what is the internal stress which comes into the device when you subject an axial load. So here the device usually will be made up of thin films only, right? So here internal stress hereafter will be represented by sigma again. So it will develop what is, it will measure what is the strain generated in the thin films. The thin film is nothing but an micro device, MEMS device. Okay, usually we use the process of lithography to etch out the material and get the required thin film. It has step-by-step process. I'll let you know in future. So all the device what we develop will be of thin films. Why? Because the thickness will be very less than 1 mm. So it cannot be a thick film. If it is above 1 mm, then it will be called as thick substrates, but it will not fall into the category of MEMS in that case. So wherever we tell device, it will be of thin films only. So this internal stress usually measure the strain generated in the thin films. If it is of macro device, then it comes into thick substrates. If it is of micro device, then it is only thin films. So you should be aware of when to use thin films and when to use thick substrates, right? So internal stresses basically helps in developing, it basically helps in measuring the strain generated in either thin films or thick substrates. So when this strain is generated, it is generated when the deformation comes into the picture, right? So when the strain has been induced, it results in formation of deformation. How you can evaluate that deformation has taken place? You cannot see that through your naked eye because the thickness of the film itself is less than 1 mm, and the human being has no so magnification in the eyes including your retina part to see that how deformation come across below the thickness of 1 mm. So we have to go for microstructure. You have to observe the microstructure of the given thin film to see any variation in the geometry. If there is any variation in the geometry, so then you can tell that there is a destruction in the original morphology due to the subjection of axial loading, and hence you can prove that there is a deformation which is caused due to the generation of strain, which is indirectly related to the internal stress. Just a second, I'm getting a call. Hello, sir. Sir, ಕ್ಲಾಸ್ ಅಲ್ಲಿ ಇದ್ದೀನಿ ಹೇಳಿ ಸರ್. ಹಾ ಸರ್, ಅದೇನಾಗಿದೆಯೋ ಒಂದು ನಿಮಿಷ ಗೊತ್ತಿಲ್ಲ. ಇಫ್ ಯು ಆರ್ ಪಾಸಿಬಲ್ ಟು ಎಡಿಟ್, ಯು ಕೈಂಡ್ಲಿ ಎಡಿಟ್ ಸರ್. ಆಫ್ಟರ್ ಕ್ಲಾಸ್ ಐ ವಿಲ್ ಚೆಕ್ ಇನ್ ಟು. ಓಕೆ. So we were dealing with respect to the internal stress. So in this, you need to check basically how the deformation is coming into picture due to the generation of strain. So that we prove by observing the microstructure through the SEM, okay, which is nothing but scanning electron microscopy. So here we have mainly two sources. What are those? One is the eccentric stress, what you have to measure, and other one is the intrinsic stress. So when we tell stress, it could be either due to external surface or due to internal stresses, right? So if the load which is subjected is an heavy load, it can hamper the surface also very badly. So this could be identified easily by the change in the microstructure. So that could be evaluated. So if you have any variation in the structure due to external surface, which is nothing but the extrinsic stress, so then you claim the source of measurement to be as extrinsic stress. If you are causing any deformation in the body internally, so then it is due to the intrinsic stress. Suppose you have a device made up of some silica. So due to external environment, if it is very humid and moisture, so if the silica gets react with that of the moisture content, and due to chemical reaction, some corrosion, yeah, erosion has happened across the surface or within the surface, then this is the damage which has been caused due to the chemical reactions. So due to this also the stresses will be regenerated and any type of deformation can happen. And sometimes due to bombardment of the light, something could be reflected and something could be incidented. So it mainly depends, because every optical characteristic equipments, either it is SEM or XRD, it what happens is the rate of electrons of different beam of wavelength will come and strike the surface, and then it gets reflected back. So it depends upon the bombardment speed with which the electron is shooted onto the surface. And the reflected ray will show you the morphology of the structure. So if this bombardment wavelength causes any variation across the surface internally, then also the damage can happen. So always we should see that what is the bandwidth of the electron through which it has been striking. You cannot blindly give the wavelength of an electron to come and shoot. You should first check what is the capability of the material to withstand the bandwidth of the electron shoot. So based on that, you should impinge the bandwidth of that electron. If it is more, then the speed with which it bombards will affect the material within the given device. In that case also intrinsic stresses will come into picture. So you should be very keen in identifying and measuring the internal stresses which are coming. So it could be either extrinsic, yeah, intrinsic stresses. So eccentric stresses could be measured only by microscopic structure. But whereas in case of intrinsic, you can observe many changes caused due to many reasons, so that you need to evaluate one by one. So this is the way how which you need to evaluate the internal stresses which is coming into picture. And we speak only about thin films because we are focusing on MEMS, not on macro device. So when a thin film comes into picture, suppose it is subjected to the compression test. So then what happens? The compressive stress comes into picture. It is not expanded due to tensile load, right? So it has been compressed, and hence the material or the device will be compressed, due to which the compressive stress comes into the picture. And always the compressive stress which comes will be expressed in a negative value. Always you should be very clear with it. The value could not be positive, it will be negative. And it could also cause buckling. So when can buckling come into picture in compression? Anyone has any idea? What happens if the given MEMS device has an smaller height, or what happens when a given MEMS device has a longer length when it is subjected to compression, when the buckling comes into picture? Any idea? Can anyone let me know? Sukrut? Sukrut, you're there?
Yes, ma'am.
Yeah. Even in previous to previous class, I had spoken something about buckling. So when you can tell that the buckling comes into picture in compression test. Suppose this is a device what you have. It has a longer height here. So if you subject for compression, you tell me whether buckling comes into picture or not. Or some device you can consider exactly half of it. So for that sample, if you subject and compression test, you tell me whether buckling comes into picture or not. That will show what you have understood about the buckling part.
Yes, ma'am. The buckling comes into matter when it is compression.
Is compression, I agree. But if the length is higher, yeah, if the height of the sample is smaller, you will get buckling, or if the height of the given device is longer, you will get buckling. What is the answer? See, you have marks as a part of
When the height,
assignment, you should answer. Yes.
when the height is length, more.
Yes, you're right. So when the length is more, so then buckling comes into the picture, right? So here also, even at micro device, you are using the same concept. Every micro device we have spoken about the thickness of it, what will be the range. But the thin film could be of very length in with respect to the length, it could have a little bit more length also. So if you have a long slender MEMS device of minimum thickness, if you are subjecting to an compressive stress, so obviously it will result in causing buckling. Buckling means you will be having a slender object. When you subject it into the compression test, it starts buckle, it gets buckled out at a particular position, right? So that is nothing but buckling. So then you have to do the buckling analysis either by using ANSYS, abacus, and check why this buckling has come into the picture. What was its mechanical properties associated? Which was the load maximum which was subjected for compression? So how did buckling occur? What was the curvature? So how do you do the analysis? Where the stress was more? Where the strain was more? Whether this buckling was due to extrinsic stress or due to intrinsic stress. So all those things you have to keep on analyzing if buckling comes into picture. So this thing you have to keep it in mind. And apart from that, if tensile stresses comes into picture, right? So if the given MEMS device has been elongated, right? So then the tensile stresses will come into picture. And always the tensile stresses value will be an positive one. That you have to remember. For compressive, the value what you consider for the stresses will be a negative value, wherein for tensile stresses, it will be a positive value, what you have to always get when you do an calculation. And if you have an excessive amount of tensile load, so then it will easily lead to the fracture of the structures. So you should be knowing when the material gets fractured and when it won't, right? So the material will get fractured if the load subjected is excessive than what it can bear for tensile stress. So then it results in the fracture. So once these concepts of internal stresses are clear enough, we are now going to apply the same old Hooke's law. So you know Hooke's law. Usually we apply this Hooke's law for isotropic materials. Okay, so here we are applying the same Hooke's law for isotropic material under biaxial stresses. It could be uniaxial stress or it could be biaxial. If it is biaxial, you will be applying the load in both the direction. If it is uniaxial, you will be applying the load in a single direction only. So that you have to understand. So with the condition of biaxial stresses, if you apply the concept of Hooke's law, so then the internal stresses will be evaluated by the equation sigma is equal to the strain into Young's modulus divided by 1 minus V. Okay, so this is the equation what we use for internal stresses. So we had one equation for for deflection of the material due to variation in the pressure for elastic properties as shown in previous case. Similarly, if you want to speak about for internal stress, you need to explain what you mean by internal stress, how it is generated, which are the two main sources of internal stress, what is the reason for extrinsic stress, what is the reason for intrinsic stress, that you have to explain. After that, you should tell that when you subject it to a thin film, when you do an analysis for a particular one, it could be either due to compressive stress or tensile stress. Then you should explain about compressive stress, how the value of the stress will be, whether it is negative or positive, and if buckling comes into picture, how you have to do the analysis. Similarly, if it is tensile stress, it will be positive, and what happens if the load subjected is more, you have to explain that it leads to the fracture of the structures. So once you explain this beautifully, then you should tell that with the concept of Hooke's law for isotropic materials. Remember that all the materials what we are using here for devising MEMS are of isotropic. It is not anisotropic material, right? So Hooke's law will apply for isotropic materials. Please remember that in mind. So as per the Hooke's law for isotropic materials, what is the condition we have put forward here for biaxial stress? In this, the internal stress will be evaluated by this equation as I told you. So this much you have to explain for internal stresses. Okay. So here it is a small beam structure which has been shown here for making your look more clear enough related to the internal stress. So I told you it is an MEMS based device, means it is nothing but micromechanical electronic system. So if you use an MEMS device of a particular length L, right? So first you will see that how the device is fabricated. So the device which is fabricated will be tested to evaluate the strain measurement. So strain measurement you are evaluating by using the concept of buckling method. So for buckling method, you have to be having at least a specific medium range of length. If the length is short, so then you cannot determine the buckling analysis. So always you will make a device of a particular length such that it is feasible to measure the buckling analysis of it. So this should be the way the structure looks like. Okay. So in order to measure the strain induced in thin films, so we will consider an double supported beam. Always, you know, if we speak about a beam, it will be constrained at one end. Means to say it will be supported at other end, and it will be supported at one end and the other end will be always free because it can move to and fro motion and the required vibrations could be achieved. But here, if you need to analyze a buckling mode, so you have to support the given beam in both both the directions, in both the ends. I'm sorry. Okay, so that is being shown here in the figure. So you'll be having the support for the beam. It is like a bridge. You have a bridge with the two supporting columns. So you have a support at both the ends. So when the load is subjected exactly at the center, axial load, what is the lateral deflection you are getting? So that you can measure, and what is the deformation you are getting, right? So that also you can identify. and any variations what you get, that also could be overcome. And if it is like in tension, so you're expanding it. If it is compression, you're compressing it. So when you compress, what is the buckling factor which is coming into picture due to the compression? So that we usually make an analysis using either ANSYS or abacus. Okay. The simulation of this could also be done in the MATLAB if you're deriving a mathematical modeling equation for the compression of an double supported beam. Okay, so it will be like m of x plus k of x is equal to some function where the deflections are coming into picture. So if you're able to make a mathematical model, you can see the simulation in the MATLAB, or you can use the workbench of ANSYS and design a simple beam structure, subject the load, show the supporting at both the ends, and then check the simulation. So it will show the buckling part of it. So you can show in the simulation how the buckling also is coming into picture. So to explain the internal stress, it's always better to show a double supported beam structure and explain the importance of internal stresses. So this is about the internal stresses. So this was a basic concept to develop the internal stress. Once the theory of the internal stress was dealt, then a person by Tabata in the year 2006, he formulated an equation to identify the buckling length of the beam. So he gave the equation as strain is equal to pi square upon 3 into T by L suffix C whole square. So this was the equation given by Tabata to see the buckling length. Okay, so here strain was referred to be, so here this one, this symbol was referred to be as strain, and T was nothing but the thickness of the film, and L suffix C was nothing but the buckling length. What is the minimum length required for buckling to come into picture? So that was evaluated by the researcher Tabata in the year 2006. So when he did this experimentally, he observed that because during the derivation of the formula there should be some assumptions, so and based on the assumptions he derived the equation and he performed the experiment also. So when he was deriving the equation, he assumed the internal stresses will be uniform along the thickness direction. So this was a basic assumption he made. So here it is nothing but the, this is the length, right, of the MEMS device. So what he told is when it is subjected to an axial load, the pressure distributed will be uniform enough. Okay, so and as a result, since the pressure distribution is uniform enough, the stresses which are being induced due to the axial load across each section of this length will be uniformly distributed. So this is the assumption what he took. So with this assumption, he determined the stress distribution along the thickness direction by varying the stress and it what is the vertical deflection you are getting. So this he just classified. So if you are not understanding, I'll repeat again. So this was the equation which was been derived by Mr. Tabata, related to strain, thickness, and the buckling length. So once he made this equation, while deriving this equation, he made an assumption that internal stresses across the device will be uniformly distributed. So this was the assumption what he made. So after that, he figured out the stress distribution. What is the stress distribution across the thickness direction? So he evaluated the stress distribution across the direction of the thickness. So how did you determine the stress distribution across the thickness? He varied the strain rate, the value of the strain. So the value of the strain was varied by varying the amount of load which has been subjected into the device. So once he applied a very minimum load, the next time he applied some medium range of load, and the next time he applied an high amount of load. So based on variation in the load, even the strain gets varied, right? And the strain gets varied depending upon the thickness of the device what we are using. So based on the thickness, even the stress which has been distributed uniformly across the length of the MEMS device also will vary. If the thickness is very less, if the load subjected is very low, then the pressure distribution will be uniform, but it will be very less. The amount of pressure subjected across each section will be very less. The same thing, if the thickness is high, the load applied is high, and the pressure distribution across each section of the given device also will be higher, and even the strain induced across each section will be higher. So he just played with the parameters of stress, strain, and thickness of the MEMS device to see that how the stress distribution and the strain distribution is varying. Okay, because all these things are essential to be evaluated as an internal stress parameters, and hence this data was uh, like compared with respect to experimental approach once this equation was derived. So if they ask you about the stresses, you should be able to explain what is the importance of internal stresses, what are the two sources, right, when it will be positive and when it will be negative, and based on Hooke's law, how you derive the equation for the stress that you should tell. Then you should explain about the buckling features by taking an example of doubly supported beam structure. So after that, when it is a doubly supported beam structure, how to evaluate the strain which has been induced in the body. So that was given by Mr. Thabata in 2006. You should tell that. So then later you have to tell he experimented that in actual, got the data, and he also played by varying the thickness direction and varying the strain to check the stress distribution across the given MEMS device, right? So all these he tested by using an cantilever beam which is supported at both the end. Don't get confused and just draw a cantilever beam which is supported at one end. It has to be supported at both the ends. So this is how you have to explain about the internal stresses, which is a part of mechanical properties in case of MEMS device. Any doubts related to internal stresses? Should I explain it again?
No, ma'am.
Okay. So kindly listen to the class carefully, then you can write in your own words. It's difficult to extract the material. Not a single book will give you all the information. You have to search for n number of books for each module. So when we are taking so much of pain in gathering and providing the useful information, kindly do listen, understand, and write well in the examination. So next mechanical property, what you have to study related to MEMS device is nothing but the strength. Once you have a material with good stiffness and less amount of stress and strain induced in it, so then obviously the strength of that material should be comparatively higher. So why I told stiffness instead of elastic property? Why? Because in elastic property we measure the Young's modulus and Poisson ratio. Young's modulus basically speak about the stiffness of the material. So it should be having a high stiffness, right? And good Poisson ratio as a part of elastic property. And next, internal stresses should be comparatively lesser. So if both the case are satisfied, obviously they should be having a good amount of strength. But how will you evaluate that the device what you have made as a high good strength? So that also has to be determined. So here what you have to think about is the strength of the material what we are using for making a device mainly determines how much force can be applied to a MEMS device. You cannot blindly just make a device and throw along like 100 kilonewton on it. Can it withstand? No, it becomes a scrap. It is a very thin film of MEMS device made up of some material which is flexible. So that material will be having some capacity to withstand the load. So you can think about to add an axial load which is capable of withstanding by that material, then only you can claim that this material has a capability of withstanding the load of this amount of Newton. So that will term the strength of that material. So in that way you can check what is the strength of a device irrespective of the stiffness of the material. And hence you should be having some measuring scheme to evaluate what is the strength of a given MEMS device. So the strength also will tell you how much is the time period for which you can rely on this MEMS device. So if you have a device what you have fabricated so nice which has capable of withstanding a load of around 10 Newton or 15 Newton, so then it speaks about what is its strength and what is the life of that MEMS device until which you can rely on it. Okay, so this reliability of MEMS device mainly depends upon some factors. What are these factors? One is the geometry of the MEMS device. What is the geometry of the device? Is it a circular membrane? Is it a square membrane? Is it a rectangular membrane? Is it a conical membrane? So it depends upon what is the geometry of the given MEMS device. So that is one thing. Second thing is loading condition. How the like what is the amount of load which has been subjected on the device and what is the conditions in which the load is subjected into the device. So these two are the main parameters which speaks you about the strength of the given material. So you should be very keen in selecting the material such that it helps in providing the required strength based on the geometry what you are going to design. So the strength of the material usually plays a very vital role that you have to think before the device has been made, and also after the device you can cross check what is the strength of it. Okay. And this is possible if it is a ductile material. Suppose if the given material what you have used is a brittle material, so then it has a tendency to get fractured easily. So if the fracture should not happen, what is the fracture strength until which the material won't get fractured? So it speaks basically when it is into tensile. So if the given MEMS device is subjected to tensile, it gets expanded until which it is able to withstand and expand. So once that limit is crossed, the fracture comes into the picture. So what is the strength within which the material can withstand the amount of fracture to occur is nothing but the fracture strength. What you have to understand. So how do you measure the flexural strength? So the flexural strength is always a measure of ultimate strength. What is the ultimate strength the material possesses? That is nothing but our flexural strength. So the flexural strength will measure the ultimate strength of a specified beam. So it depends upon what is the beam material you're using, what is the length of the material, what is the length of the beam you're using, and if it is supported at both the end, what is the way it is being supported, what is the amount of load which has been subjected. So each and everything will count here. So based on the loading the bending can come into picture and even deformation can happen. So this is for elastic materials. If you have any material which is inelastic, means plastic material, so this will yield strength. Okay, so in this case, the yield strength is defined as specific limiting deviation from the initial linearity. What do you mean by it? So if it is an elastic material, inelastic material, when the load is subjected, it gets deformed, but it cannot comes back to its original position. So then, in case of plasticity, we usually refer for the yield strength. So that is the maximum strength the material can bear in before it gets into the plastic stage. So once that has been crossed, it moves into the plastic range where linearly, but wherein it cannot come back to its original position. So that is the yield strength. What is the yield strength of the material it can bear before it goes to an plasticity range? So that also you should be able to figure out the actual strength. The yield strength value has to be known. So with the help of strength of the material, you can check what is the reliability of the given MEMS device. So one will be very careful in determining the yield strength as well as the strength of an material. And lastly, the tensile strength. You should be telling how you can define it. You know that tensile strength is defined as a maximum stress the material can withstand. What is the amount of stress a material can withstand before a complete failure comes into picture? So if you start keeping on expanding, finally a complete failure can come into picture, right? But wherein the compressive strength, what you will determine will be related to that of brittle materials. Tensile strength comes into picture in case of ductile material where it can elongate until its limit before fracture comes into picture. But whereas in case of ductile material, it can compress and expand, it can compress and expand, it can deform and come back to original position. So this is related to that of a brittle materials. So if they ask you about the strength, you should be able to tell how you define the strength of a material, what is the need to evaluate the strength of a material, and how it is useful to measure the strength in case of a brittle material as well as an inductile material. So how you evaluate the yield strength? So yield strength will come into picture when it has crossed the elastic limit. So at inelastic nature, how you evaluate the yield strength of a material? So this much you should be able to explain related to the strength properties of the related to the strength factor of the mechanical properties. Any doubts related to the strength factor of MEMS device? Any doubts? Okay, if that is clear enough, you should be knowing the last property of MEMS device, which is nothing but fatigue. So everywhere you have heard about the word fatigue, stress, strain, right? So all these comes under the mechanical properties of a material when it is subjected to some specific loading. So when you call it is an fatigue, can anyone tell how do you define fatigue? What do you mean by fatigue? Even the human being can feel that I am feeling very fatigued today. So when a person feels fatigue, any example for it? Anyone can tell me the answer? Answer me please. When you can tell that it's a fatigue.
When it's low strength or low energy.
When the strength is
Low. It
low.
can't withstand. Material can't withstand the strength.
Material can't withstand the strength or the load. What is it?
Material can't withstand the load and it has low strength.
Okay.
It under.
Yeah, so fatigue usually comes into picture when the material has a low strength, but you are subjecting a load which is like an higher one where a weak strength material cannot bear. So in that case, a fatigue thing comes into the picture. So this type of fatigue comes into picture in case of our MEMS device when we expose it to the cyclic or constant stress. What do you mean by that? You're subjecting a continuous amount of stress into the body, or cyclic frequently after every cycle the same thing has been repeating. So the body feels it is fatigue, means you're doing the same type of work from morning to evening. You feel that you are under fatigue. Means you don't have relaxation. Continuous amount of loading without any relaxation will result in the formation of an fatigue. It could be either to a machine, it could be either to a MEMS device, yeah, it could be either to an human being. Every device or a human being can work, but not for a continuous period of time. There should be some relaxation in between. If that doesn't happen, and if you're doing that kind of work for a longer period of time, suppose you don't sleep for 2 days, you are working continuously 24 by 7 for 2 days. So after these 2 days, how do you feel? Whether you feel relaxed without any stress and strain, or you feel like you are feeling something fatigue. So I'm not able to do anything. I'm feeling restless. So this happens because you're working continuously without any break. The same thing will happen in case of MEMS device also. So if you're subjecting this axial load continuously, or you're subjecting this load in a cyclic manner frequently and regularly, and that too not for short period of time, for a longer period of time, so then it results in fatigue. Okay, so such operations usually results in the formation of fatigue or inducing a fatigue in an device which is working for a continuous period of time, which is subjected to loading. And be careful, loading, I'm telling, it is not like an heavy loading, medium, or small range of loading. If the load, what we have subjected, is continuous for a long period of time without any rest, then it induces fatigue in the body. So, this type of fatigue could be observed as a drastic change in elastic constants. So when you have a material, it will be having elastic property and plastic property. It will show its elastic nature until particular point where yield strength is reached. So then it goes for plasticity. So where the plastic deformation happens, it won't come back to its original position. So, this type of fatigue can be observed as a drastic change in the elastic constants as well as in the plastic deformation. So, this will make the MEMS device to be very sensitive, and it can also result in drift in MEMS device. So there could be a sudden drift in the MEMS device. It can get hanged out. It is not working properly. Why? The MEMS device might be operating continuously for 24 bar 7 without any rest time. Right? So then you can tell that there is a drift in the MEMS device. Hangout due to fatigue, because you are subjecting to constant stress or cyclic type of stresses, that too frequently for a longer period of time. So this is just an example of how a fatigue comes into picture, right? And if a fatigue is there, you can also observe that the strength of the device decreases. It's not like the regular strength and stiffness what you had in that device will retain. No. Once the fatigue has come, when the device is down, once a drift is there in the device, even though the MEMS device was very strong enough in the beginning, we can observe that after this hangout, there will be an reduction in the strength. And due to this sudden reduction in the strength, the drawback is it may lead to fracture accidentally. And once the fracture comes into picture in a device, accidentally without any notice, it results in the failure of the device. So that device could not be used further, right? So you should not at all make see that the MEMS device is subjected into fatigue. Once if it is in fatigue condition, the strength of the material will be reduced. So due to this, even though you apply the load which was feasible enough for that device, it won't be able to withstand because the strength has been reduced. So the minimum amount of load what you subject also will not be bearable, and finally the device gets failed because it leads to fracture. So this is more dangerous. You should not always, you should never see that the fatigue is coming into the picture. It is harmful for the devices as well as to the human beings also. So be careful and you should explain properly what happens if fatigue behavior comes in picture. And apart from the failure, you have two more parameters what you have to understand. So the fatigue behavior of a MEMS device, how does it vary? So it mainly depends upon the size of the device, what is the surface effects which is causing fatigue, and also the effects of the external environment. External environment means it is speaking about the humidity aspect, temperature, and the resonant frequency. Suppose if you have a cantilever beam and it is subjected to high amount of moisture, and if the temperature is varying very frequently, and if you have the modes of frequencies at the resonant very frequently, right? So this might also lead to the fatigue of an MEMS device. So apart from that, it also depends upon the geometry. What is its dimension? What is the length of the cantilever beam? What is the size and thickness of it? How the surface has been protected, right? And how it is responding to the external stimuli of the environment. So all these factors also will claim what is the fatigue behavior of that particular MEMS device. And lastly, I want to tell you, if you want to make the devices to be reliable highly for a longer period of time, you should see that that device is free from fatigue behavior. You should never come across making a device towards fatigue. Bringing a device towards fatigue is nothing but bringing a device towards the end of the life. If fatigue comes into picture, the strength comes down, obviously it gets scrapped out, fracture comes into picture, and the life of that device comes down, and you cannot tell that this device could be reliable for future. So always you should be careful that any device for that matter, it should not come across the fatigue. So this is also very important property, mechanical property associated with our MEMS device. So here I will just stop. From next class, we will be dealing with scaling of mechanical systems. So now we have just covered one title here related to mechanical properties of MEMS. What is its importance, right? Why we need to evaluate the mechanical properties? Which are the mechanical properties? These are elastic, right? Then internal stress. Then we spoke about strength and fatigue. In case of elastic also we had two properties which are Young's modulus and Poisson ratio. So you should be able to explain all these four properties beautifully relating to the MEMS device. So that will show the importance of mechanical properties in any MEMS device. So these things you should explain carefully. Any doubts related to this, please kindly let me know. Hope the things are clear enough. Any doubts?
No, ma'am.
Okay, if so, is it the same from others also? I'm getting response only by Mohan Ambal. What about the others? Is it clear enough?
Yes, ma'am.
Oh, okay. So then in tomorrow's class, we'll see what is the importance of scaling a microelectromechanical system. Means we are scaling down the dimensions. It could be either with respect to the stiffness, the strength, the geometry, the temperature parameters, or anything else. So that we will be dealing in the next class. So that is an important part what you have to understand. So today's class in 2 hours class, we have covered all the basic concepts of MEMS, the importance of mechanical properties, and what are the main mechanical properties, how we can evaluate from a device which is made, and what are its importance. So these things please keep in mind so that you can explain well in your internals as well as in your examination. So now all of you can write your name and uh, USN number in the chat room. I will just call the attendance. Dhanush,
Yes, ma'am.
Mithun,
Yes, ma'am.
Mohan Ambar,
Yes, ma'am.
Sandesh. Okay, Sandesh has written. Srinidhi, 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 you're there? Srinidhi, I think he's
It's not there.
okay. Sukrut,
Yes, ma'am.
okay. And Harsha.
Yes, ma'am.
Yes, so everyone, we will see tomorrow with respect to scaling part, which is nothing but miniaturization of a given MEMS device, of a given device. It's not MEMS device. The actual device, when we scale out or when we do the miniaturize, then only we get the micro electromechanical devices. So that I'll be presenting in tomorrow's class. So see that all of you attend the classes regularly. We will meet tomorrow by 9:30 then. Until take care and have a nice day.
Thank you, ma'am.
Yeah, yeah. Thank you. Bye bye.
Thank you, ma'am.
Yeah, thank you. Yes, okay.
Thank you, ma'am.
Yeah, bye. Take care.